So here, my dear friends, welcome to this discussion. We are going to be discussing calculations on pH of buffer solutions. So number one says, what is the pH of a solution consisting of 0.75 molar ethanoic acid and 0.5 molar sodium ethanoate? The Ka, or the acid dissociation constant of ethanoic acid, is 1.8 times 10 to the power negative 5. So we know pH of any buffer solution according to Henderson-Hasselbalch equation. A pH is equal to pKa plus logarithm of A minus, that is if it is composed of a weak acid and its conjugate weak base. So here I'm going to be getting the conjugate weak base divided by the weak acid, Ha. So what is the concentration of the conjugate weak base? And what is the Ka value? So this is pH, which will equal to negative logarithm of Ka plus logarithm of the concentration of the weak base. The conjugate weak base is sodium acetate, which is 0.5 molar, divided by 0.75 molar. This is pH, or potential of hydrogen, equal to negative logarithm of 1.8 times 10 power negative 5 plus logarithm of 0.5 out of 0.75. This gives us 4.57. So, but what is the pKa? pKa, this value here, is equal to 4.92. So it is evident that if we have more of the acid, then the pH value is going to be less than the pKa value. And likewise, if we have less of the acid, then the pH value is going to be greater than the pKa value. Next question, what is the pH of a solution containing 0.15 moles of ammonium chloride and 1.5 moles of ammonia? Take Kb of ammonia as 1.8 times 10 to the power negative 5. Here we are having a weak base, ammonia, and its conjugate weak acid, that is ammonium chloride. So we are going to use Henderson-Hasselbalch equation that gives us the pH equivalent to pKa plus logarithm of the concentration of the weak base divided by the concentration of its conjugate weak acid, Hb. Now, what is pKa? This is equal to 14 minus pKb. So can we determine that this is equal to 14 minus the negative logarithm of 1.8 times 10 to the power negative 5. And then pKa becomes 14 minus 4.7443. This gives us 9.25527. Now, what is the pH? That is 9.25527 plus. Now, logarithm of the weak base is ammonia, that is 1.5, divided by the concentration of its conjugate, weak acid, which is 0.15. So this gives us 10.255. So you can see that the pH is greater than pKa, and we said that if the pH is greater than pKa value, the solution is from a weak base and its weak conjugate weak acid. So this is as expected. So next problem is to calculate the solution containing 15 grams of hydrofluoric acid and 21 grams of sodium fluoride in 750 milliliters of a solution. The acid dissociation constant of hydrofluoric acid is 7.2 times 10 to the power negative 4. So here we are going to be determining the pH of this buffer solution containing a weak acid and its conjugate weak base. Now we have 15 grams, and all of this is in 750 milliliters of a solution. So we are going to be looking for the number of moles per liter of the solution. Now we know that the molar mass of HF will be 1, atomic mass for hydrogen is 1, and for fluorine is 19. So this gives us 20 grams. So number of moles is equal to mass given divided by the molar mass. So this becomes 15 divided by 20, and this is 0.75 moles. So we shall say that 750 milliliters of solution contains 0.75 moles of HF. Then what about 1,000 milliliters? It should be 0.75 divided by 750 times 1,000, which gives us 1 mole per liter. So this gives us 1 molar. Then let's talk about the concentration of sodium fluoride. So sodium fluoride, the molar mass of sodium fluoride, this is equal to 23 for sodium plus fluorine, that is 19. This gives us 42 grams. So the number of moles will equal to mass given divided by the molar mass. This would give us 21 grams divided by 42 grams. And this is giving us 0.5 moles. So these moles are present in 750 milliliters of the solution. So 750 milliliters of solution contains 0.5 moles of sodium fluoride. What about 1,000 that we are interested in? Becomes 0.5 divided by 750 times 1,000. And this is giving us 0.667 molar. So what do we do next? Using Henderson-Hasselbalch equation for determining the pH of a buffer solution. So pH will be pKa plus logarithm of the concentration of the conjugate weak base. And this is going to be negative F, that is the fluoride ions. Equation to determine the pH of a buffer solution, this becomes pKa plus logarithm of the conjugate weak base divided by the concentration of the weak acid. So pKa is equal to negative logarithm of Ka value, and this is negative logarithm of 7.2 times 10 to the power negative 4. And this gives us 3.1427. Then what about the concentration? Logarithm of the concentration of the weak base, the conjugate weak base is 0.67. So concentration for the conjugate weak base is 0.667 divided by the concentration of the weak acid, which is 1. So this gives us negative 0.176 and 1. So pH becomes 3.1427 minus 0.17. And this gives us 2.967. And again, pH is less than the pK value, which is expected. This is as expected because we have a buffer solution made from a weak acid and its conjugate weak base. Next question says, what is the pKa of an unknown weak acid if the pH of the solution was measured to be 5.62 when the concentration of the weak acid is 0.45 molar, and then the concentration of the conjugate weak base is 0.85 molar. So let's look at the solution. We know that pH is equal to pKa plus logarithm of the weak acid the weak conjugate weak base concentration divided by the weak. So let's look for the pKa. This will equal to pH. The pH is known as 5.62 minus the logarithm of the concentration of the weak base is 0.850 divided by 0.45. This is 5.62 minus 0.272 as pKa. So pKa will be 5.34. So this becomes the value of pKa, or the acid dissociation constant of the unknown weak acid.